Hi folks, this is Linear Algebra Take Home 4. We're given a set of two vectors, two polynomials in P2. We're asked to prove that the set's linearly independent. So there's two ways to proceed here. We can do the old linear combination approach. And prove that the only C1 and C2 that work are going to be C1 equals C2 equals 0. So the only linear combination that gives you the trivial vector, the zero vector, is a trivial linear combination. So we could certainly do that, and that's not that hard to do. Or we could use the fact that we only have two vectors here. And so for a set of two vectors to be linearly dependent, we know that only happens when one is a linear combination of the other. Well, what's it mean for one to be a linear combination of the other in this case? It means one is a multiple of each other. So this is linearly dependent if and only if u and v are multiples of each other. So that means that this is linearly independent if u and v are not multiples of each other. So let's look at this polynomial, t squared plus 2t plus 1 compared to t squared minus 3t plus 1. Well, they're clearly not multiples of each other, because the multiple would have to be 1 to get the leading term and the constant term to work out, but that doesn't make the middle term work out. So I'm just going to choose the easier route here, and I'm just going to say since t squared plus 2t plus 1 and t squared minus 3t plus 1 aren't multiples of each other, x is linearly independent. Now that only works when you have two vectors. If you have more than two vectors, you have to go through some sort of rigmarole. Now in part B, we're asked to find a basis for P2 that contains x, and then we need to prove the answer is in fact a basis. So what do we know about P2? We know that the basic, or the standard basis for P2, t squared t1, there's three of those vectors, so that means that the dimension of P2 is in fact 3. So what I need to do is add a vector into this group that's not a linear combination of what's already in there, and then I'll have 3 linearly independent vectors and I'll be done. Okay, so I need to know what things are linear combinations of those two vectors, which means I need to figure out what the span of x is. So I'll just look at linear combinations here. And if I combine the like terms here, I get c1 plus c2 t squared plus 2c1 minus 3t c2 t plus c1 plus c2. And so what I need to do is find a polynomial that's not going to fit that pattern for any choice of c1 or c2. I could pick a c1 and a c2 and then just pick something that's different than what I would get. You know, two of them the same, one different. But the one thing I notice about this is that I've got the same, whatever number is there has to be the same number there. So that leads me to try this vector. Let's just make a 2t squared, say, plus 1. Can that possibly be in the span of x? Well, the answer is no, because c1 plus c2 would have to be 2, but at the same time it'd have to be 1. So here's one that I claim will work. So the basis B I claim is t squared plus 2t plus 1, t squared minus 3t plus 1, and 2t squared plus 1. Now how do I know this is going to be a basis? Well, I've just shown that this is not in the span of these two. And we had a theorem in class that says if u is not in the span of x, then x append u is linearly independent. So since 2t squared plus 1 is not in the span of x, x union that is linearly independent. Since the dimension of P2 is 3, x union 2t squared plus 1, which has 3 vectors, must be a basis. That's one way to prove it's a basis. Another way you could prove it's a basis is to take those 3 vectors, take their coordinates, put them in a matrix as columns, and take the determinant, show the determinant is not 0. Okay, or any of the other ways we've talked about doing it in class. But once again, you want to make good use of these theorems. The theorems are the power tools, and if you understand the ideas, it'll save you a lot of computation. That'll do it for Take Home 4.